Hello and welcome back to Calculus 1. There we go. I ruined that. All right, it's from scratch. Hello and welcome back to Calculus 1, section 2.5, limits at infinity. There we go, much better. And I'm not going to edit that, so you'll have to listen to it twice. Last time we talked about infinite limits, where we expected answer to be infinity, and that eventually led to the concept of vertical asymptotes. Because for the vertical asymptote to exist, when you approach the x value at which you have vertical asymptote, y value tends to go to infinity. Now, for limits at infinity, you are examining the limit at infinity. So we are looking at the problems which have this form: limit x goes to either positive or negative infinity of f of x, to give us either finite value L or one of the infinities as the answer. So this is what we are dealing with in 2.5. Now, both of the concepts that are covered in this section as application of this are some concepts that you learned in your pre-calculus course. The one on the, let's use pink, green. So the top one here will be the horizontal asymptote, and the one on the bottom is end behavior. So those are the two concepts that we will deal with. Let's start with the end behavior. As we analyze functions, we can look at the part of the function that will, in quotes, go to infinity, that will forever continue in whatever fashion we have it. So for instance, if you take a look at the basic parabola, we put these arrows at the end to signify that this line will forever go up like that, beyond what I'm drawing. We also put arrows on x and y axis to signify that they will go forever in that direction. So for this parabola, these ends that I have, so the two ends that I have here, this end and this end, so those are called end behavior. Looking at the possibilities, you may only have 4 of these. So here are the possibilities. The function line could always go like this, that, like that, or like this. So you know that if you have these two, they are creating a cubic function, or x to the 5. If you go the opposite way, they create negative x cubed, negative x to the 5, negative x to the 11. These two could be x squared or x to the 4th or whatever. So you have this end behavior which is going to follow. For instance, if you just consider this one, it's a square root of x, because the square root of x starts at the origin and just goes like this forever. So that belongs there. So we have these 4 combinations, right? And then there is a limit that explains mathematically each one of these. So for this guy, so this is your y-axis and this is your x-axis, right? So for this guy, in the upper right corner, the quadrant 1, you have the limit x approaches positive infinity, because you see that x goes, right, this this motion, this arrow, can be decomposed into motion to the right forever and motion up forever. So as you decompose into these motions, you see that as the x goes forever to the right, the y value goes to positive infinity. So this is both positive infinity, positive infinity. As x goes to positive infinity, y goes to positive infinity. Now one below, limit of f of x, x still goes to positive infinity because it still goes to the right. But the answer, the y value, goes down forever. So that's negative infinity. And then you have 2 on the left. So the upper one is limit. X goes to negative infinity now, to give you positive infinity as the answer, because it goes forever to the left and up. And the one on the bottom is limit f of x, and that's going to go to negative infinity. So these are the 4 possible end behaviors that you can have. Now they can mix with vertical asymptotes, and they can mix with the horizontal asymptotes and so on. So a mixture, an example here, the mixture would be if you consider function y equals ln x. So the graph over here, this is the ln x graph. And you know that the ln x has a vertical asymptote. So this side is the vertical asymptote because limit as x goes to 0 plus of ln x is equal to negative infinity. That fits the definition of vertical asymptote from last class, where you are approaching finite value from either left or the right, and you are getting answer to be infinity. Now the other side of the graph, so this side of the graph, is our end behavior, and it's the upper one. So over here, the limit as x approaches positive infinity of ln x is giving you positive infinity as the answer. So that's the mathematical way to describe the end behavior of the function through the limit. So for ln x, you see it's a combination of the vertical asymptote on the left, which we see again approaching a finite value from the right, and the answer is infinity. And then for this one, you have 2 infinities here, which is called as the end behavior. And that's the end of the story for end behavior. Now you can draw any function you want. What's the end behavior for sine and cosine function? Is it going to be any of the infinities? No, because they oscillate between -1 and 1. So what are the functions that exhibit this behavior? Well, clearly all polynomials. Pick x to 17 minus 3x plus 5. Great. That's going to be the one of them. And then you've seen it on ln x. You can also do this for e to the x, right? So square root of x. It doesn't work on trig, right? Tangent graph for trig. Tangent graph has all of the asymptotes, vertical asymptotes at every pi over 2 plus minus pi. So it's not going to fit the end behavior there, the way we presented it here. So that's the end behavior. Now, what we are more interested in is the concept of the horizontal asymptote. Now, I know that some of you still remember what you learned in Pre-Calc 1 with comparing the powers for the rational function to find a horizontal asymptote. And that still stands, but you don't actually need to know it anymore because we're going to now do the limit definition for horizontal asymptote. But What you learned earlier is that if you have p of x divided by q of x, where both are polynomials, you have your rational function, and then you have your x to the p divided by x to the q, and then a and b coefficients in front. These are the leading terms of p and q polynomials. And then you had those three cases which you had to memorize in your pre-Calculus 1 course. If p is bigger than q, no ha, right? No horizontal asymptote if the degree of the numerator is larger than the degree of the denominator. If p is equal to q, your horizontal asymptote is at y equals a over b. So ratio of the coefficients. And finally, if p is less than q, horizontal asymptote was at y equal to 0. So this is something that you learned in pre-calc 1. This is still valid. You can use it. But the little issue we have with the calc 1 now is that we are not only considering polynomials, right? So it's not enough for vertical asymptotes. It is nice and cute, right? It works for polynomials, but we are going to see that the definition that we give covers this, plus technically anything else that we have with functions. So let's go do the definition of horizontal asymptote. Definition of horizontal asymptote. So, if f of x if limit, there we go, if limit f of x as x goes to positive or negative infinity is equal to L, then f of x has a horizontal asymptote at, now spell it out, y equals L. Otherwise, it does not have horizontal asymptote. All right. I want to test this immediately on one of those pre-calculus examples where you memorize all the rules, just to make sure that all this fits. So, consider pre-calculus 1 function x minus 3 divided by x squared plus 9. If you set your denominator equal to 0, you will not find any vertical asymptotes. Because x squared plus 9 equals 0 does not have any real solutions. So no vertical asymptotes. But we are interested in horizontal asymptotes. So all I need to do is to take the limit as x goes either to positive or negative infinity. So I'm just going to put positive there. Of x minus 3 divided by x squared plus 9. And I need to solve this. Now this is going to be a new way to solve problems. If you have polynomials, you are supposed to divide every term by the highest, with the term with the highest exponent. So this is the procedure now. And guys, this is what you learn, all right? So it's new. What I'm going to do is I'm going to divide x minus 3. You see how I leave some space? Because now I'm going to divide it by x squared. Then I go into denominator, have x squared plus 9, and I'm going to divide each one by x squared. So I'm dividing with the highest power, right, that is available in the entire problem, which is x squared. So now this is equal to limit x goes to infinity, and now just use the algebra. 1 over x minus 3 over x squared divided by 1 plus 9 over x squared. And for the time being, which I have to explain to you soon, every single one of these is going to go to 0. And I'll explain why shortly. So what you have is 0 divided by 1, which is 0. And we know that we have a horizontal asymptote at y equals 0, which is exactly what we expected from your pre-calculus rules, where you memorized that if the higher exponent is in the denominator, your horizontal asymptote is at y equals 0. So it matches. And now let's go back and consider all of these things that I crossed out. Before we do any of that stuff, let's take a look at the limit of 1 over x as x approaches infinity. So what do we get? Well, by what you see up there, you should get 0, right? If you consider the term where it went to 0. It's the same problem. Now, I am going to look at the graph and determine that, and then we can also do the chart and determine that. Do you see that as you are going to positive infinity, that your y value is going to 0? Do we see that motion if you're staring at the graph? Picture yourself walking on this. Here's your hat. Now three people with hats are going to try to figure out which one I drew. So we have, right? So you see that as you are going always to the right, you're coming down a hill and your y value is 0 at infinity. Do we all visually see that? You need to be able to pick those things up from the graph like this. So as x goes to positive infinity, y is going to go to 0. So the answer is 0. And the limit of 1 over x squared as x goes to infinity is also 0 with accompanying graph right there. From where I'm going to extrapolate that limit as x goes to positive or negative infinity of 1 over x to the n is 0. And yes, you are going to use this a lot. I don't like this red color. It's too dramatic, and it's good. So highlight that one. Now, as soon as you know this, you immediately go, okay, 1 over x, and the next one is 3 over x to the n, but n is 2, so all of them go, and that's great. Now, I also want a physical, I want you to visualize this, and I'm happy that we have this in the classroom. All right. Behold one paper. All right, this is one paper. And what I have here is a division of one paper. We're going to learn a lot of different things now with this. Mathematical concepts, click in. I am dividing one paper into a number of piles. If I want to divide by 2, in the physical realm, dividing by 2 means take whatever you have and put that into 2 equal piles. So I have 4 markers, I create 2 piles, and I keep assigning markers to those piles until I run out. So 4 divided by 2 is 2 in each pile. So what is the denominator? The denominator is the number of piles. Number of physical piles when you start dividing. If I want to divide students into groups here, well, you better have a place to pile up, right? Group up. So, you know, a pile of 3 students right here, group, but, or a pile, whatever. And then a 3, and then a 3, and then a 3, and then 3, 3, 3, 3, 3. Great, you're divisible by 3, nice. So, the denominator is the amount of physical piles. If I want to work on dividing by 2, what I need to do is to create 2 equal piles, and then it's me dividing this paper by 2, and each one of these pieces now is a half. So that's what the meaning of 1/2. So the half is the result. Left side would be 1 divided by 2 equals a half on the other side. Now see, this side is the answer. So if I'm dividing 1 into 2 piles, I am getting a half on the other side. Then you go on and you get your quarter. So that's 1/4. Now, and then if you divide by 8, this piece is an 8. And this piece is a half. What can you tell me about this piece in comparison to this piece? It's smaller. Good. So, the more piles I have, the result is getting smaller. It should click by now that if I'm dividing by 16, because I divided an 8 in a half, and I get 16th, 32, 1/64. There are 64 of these in that big piece of paper that I initially had. So I'm dividing one paper by 64, and I'm getting 1/64th on this side. The answer is this physical size paper. What is going to happen with this paper? Here's the 128 and 256. Look at that, 256. 256 of these in the big paper we started with. So 256, what do I have? What's going to happen if I keep dividing this forever? Now I'm at 512 of these pieces in the full paper. What is happening with the result? Yeah. So if I infinitely divide this, what's going to be the answer? You see that? Now, going back to my previous question over here where I put all of these, go to 0, go to 0. Would you agree that if I have one paper or if I have 3 papers, would it matter how many papers do I have? No, it doesn't, right? It doesn't matter how many papers you have. You can have 50,000 papers. If you divide them with infinity, the answer is going to be nothing, right? So that's physical mechanics behind the formula you see. You are going to divide. Now, clearly, the higher exponent you have here, it's going to go to 0 faster, right? So it's 1/2. If it's 1/2 squared, it's a 1/4, so you're dividing by 4. So it's going to go to 0 faster. So now, oh, I forgot to write, this is important, that n must be bigger than 0, right? Positive n's. Because if you have a negative n, it goes into the denominator and this doesn't hold anymore. So make sure you add that. One more concept that is not needed for this lecture, but it's still when we're talking about this. Guys, notice that the idea that I just told you where you are dividing and you're creating physical piles, your denominator cannot be 0. You see why? If I want to divide this classroom, right, all of you, into 6 groups, perfect. Give me 6 captains over here, and then you guys start picking, and eventually we'll have division of 6, right? Can I divide you by 0? That means get 0 captains over here and let them do the picking. You see how insane that is? You cannot take an object and divide it into 0 piles. See, this object is in 1 pile already, and that's your base reality. You cannot divide this by 0 because that means you are trying to take this object and assign it in 0 piles. I can assign it in 2 piles, right? And that's simple. Here. So one object is now in 2 piles. And I can get you any number of piles. It's okay. But I can't get it in 0 piles. It physically exists. And I can't take something that is already 1 pile to go into 0 piles. Now, hopefully you also, with this, now you understand why we don't like square root of 3 in denominator. Square root of 3 has a non-ending decimal, which means, well, that's not 2 piles or 3 piles. It's a never-ending decimal, so it's actually a pile that cannot be defined as a finite pile. Any other finite decimal is okay because you can multiply top and bottom by 100 or 1,000 or 50 million, whatever, and get rid of those decimals and then have it as a 1 pile or whatever. But the square root of 3, square root of 2, or any irrational number which does not have a finite amount of decimals cannot give you the finite amount of piles, so we don't like them in denominator, right? So all this talk about the division hopefully put all of the concepts and a lot of concepts together for you to see. And now, going back to the example I did, when you are dividing polynomials in the limit that goes to infinity, which is the horizontal asymptote definition, you will divide by the highest exponent everywhere. And then once you simplify the algebra, every single one that has the x's in denominator is going to die because of our formula that we wrote down there. And you have 0 divided by 1, which is 0. Cool? Of course, it's cool. It's calculus, right? This talk should be like number 1 when someone asks you, hey, what's new? Paper, pencil, pull up the chair, man. Let me show you. We did this in calculus on Thursday. You can finally now tell someone why they can't divide by 0. Good. So I'm going to steal some of the examples from the textbook. Because lecture is over, I just need to do a few examples. We're done. Number 10 says, limit as x goes to infinity of 5 plus 1 over x plus 10 over x squared. So what is this equal to? Robin? 5. Good. Because as you divide one piece of paper by infinity, it's going to go to 0. When you divide 10 pieces of paper by infinity, it also is going to go to 0. So the answer is simply 5. Beautiful. Question 14 says, limit of x goes to negative infinity of 5 plus 1 over x plus, look at this now, sine to the fourth of x squared divided by x to the, no, x cubed up there, and then x squared here. What is this equal to? Yeah, why 5? Sure, I agree this goes to 0. Now, why is this 0? Can anyone tell me? What's the magic word? Why is this 0? You're right, it is 5. Good, great, yeah, sure. Why? I'm like a 5-year-old now. They don't say why, they say why. Why? The trick that solves it we talked about it last class. Yeah, the sandwich thing, yeah, sure. But we're not going to use the sandwich theorem to solve this, but the concept, the function that we dealt with within the sandwich theorem, the same concept is popping up here. What do we know about sine and cosine functions? Beautiful. They're bounded by 1. So the entire the entire numerator here is as good as 1. It can't be bigger than 1. So it's bounded. So I'm just going to say over here, sine x, cosine x are bounded by 1. So technically the term is 1 over x squared. So yeah, it dies too. So you have 5 plus 0 is 5. That could be the trivia question next time you go out, and right? Yeah, all of you that missed the opportunity to bring it up last night. Huh? By next year, man, it's going to be Calc 2 as well. And some really nice stuff there. It's amazing. All right. Function given, this is problem 28. So function given is 4x squared minus 7 divided by 8x squared plus 5x plus 2. And the question is, do we have any horizontal asymptotes? By the way, if you write horizontal asymptote is equal to 3, it just triggers my allergic reaction, and because you're not close, right, I just go like this. Because that's not an equation. Equation for horizontal asymptote is y equals 3, y equals negative 5, y equals whatever. So do not put horizontal asymptote equals 3 and then think you achieved something. Strong. Do we have any horizontal asymptotes here? What's the procedure? What's the definition? Anyone? See, this is why I'm depressed. I mean, you know, classroom of 30 and I get ignored by everyone. I asked you a question, you know, to bond and stuff, and it's just... Oh.
Because the degrees of the doubt are the same. That's the whole.
From pre-calc, yeah, but what are we going to do with the definition we did? Mm-hmm.
Degree of numerator equals degree of denominator.
Yes, that's exactly what I put up all the way at the beginning, reviewing, right? So right here, if you want to, right, quote that, that's that part. But then I also said this, which we don't have to worry about memorizing the black one if we know the red, purple, pink, magenta. Someone said magenta. I will never forget that word. It sounds like type of a blender or something. But apparently it's supposed to be color similar to this. This is pink. I know pink. This is pink. That's pink. So that... whatever. That's the reason why I do math. It's the equation for everything, and we don't have to debate things. At one point I heard someone in Home Depot say it's off-white.
So
Yeah.
It's at 0. It's at 1.
So we're going to do the limit. X goes to infinity. And then you just do what we did earlier. What is the way to solve this?
Divide everything by the highest.
Perfect. So, divide everything by highest. Divide by x squared, divide by x squared, divide by x squared, divide by x squared, divide by x squared. That's the highest. Limit x goes to infinity. 4 minus 7 over x squared divided by 8 plus 5 over x plus 2 over x squared. This one dies, this one dies, this one dies. What's left? Yes. So, horizontal asymptote at y equals 1/2. This is the calculus way to show that there is the horizontal asymptote at 1/2. Your homework question, exam question, final exam question might state for this problem, show that f of x equals the whole thing is y equals 1/2. You see? The answer is given to you, so it's completely pointless. So it's like, oh yeah, the degree and stuff. No, what they're asking is to do this, to show that you know the definition for horizontal asymptote using limits, and then crank it. Fair? Welcome to Calc 1. I know, right? Just like a Jeopardy, we first did the whole thing and then it was like, okay, this is the question. You're gonna love this one. Right? 41. I'll jump right into the limit because... Right. 4x cubed plus 1 divided by 2x cubed plus square root of 16x to the 6 plus 1. And probably most of you are going, but why? Because we can. What's the highest exponent? 3. What's going to happen to x to the 3 when it undergoes the square root? What's going to happen to it? Yeah, it's going to become x to the 6. Very good. So the highest exponent is x cubed, because if I divide everywhere by x cubed, if I divide the entire thing by x cubed, when it goes under the square root, it will pick up double the exponent, so it's going to become x to the 6th. All right, so limit x goes to infinity, and now I have 4x cubed plus 1 divided by x cubed each. In the denominator I have 2x cubed plus square root of 16x to the 6 plus 1. And now I have divide here by x cubed and divide here by x cubed. Now, note the spacing over here, that the division line is longer than the square root, right? In the next step, they're going to swap positions. So now limit x goes to infinity. These guys cancel in the numerator, so it becomes 4 plus 1 over x cubed. In the denominator, we just have 2 plus, and now the square root becomes deep, so that we can have 16x to the 6 divided by x to the 6 plus 1 over x to the 6. So at this point, x cubed went under the square root and became x to the 6. If you, what's the square root of x to the 6? X cubed, right? So, right? Think about it. And now these guys will cancel. So in the next step, limit goes to infinity. 4 plus 1 over x cubed. 2 plus square root of 16 plus 1 over 6, x to the 6. What's happening in the next step? This dies, and this dies. So what's left? 4 plus 0 divided by 2 plus square root of 16. Clearly 2/3, right? Good. And you have problems 42, 43, and 44 to enjoy on your own. Some of these have the cube root, some of these have, yeah. So you can enjoy the rest. By the way, horizontal asymptote at 2/3, right? So horizontal asymptote at y equals 2/3. Because the limit going to infinity gave us 2/3 as the answer. When it gives us 2/3, we know it's finite value, so that's the horizontal asymptote. If it gives us any of the infinities, it's the end behavior. The last thing we are going to take a look at is decay model. You guys learned this in your pre-calc 1. Y equals AE to the negative KT. Decay model. You used it for what? Carbon dating to see how old an object is. You used it for decay of garbage, for environmental issues. You use it for nuclear decay, for environmental issues again, nuclear waste. You used it for the decay of the particle. You used it also to metabolize the drug in a body. All of these problems had half-life in it. To metabolize the drug in a body, so biological life of Advil is 1.9 hours, which means that in 1.9 hours, half of the dose of Advil you took, if you took the prescribed dose, like 2 pills or something, the half of that will metabolize and the half stays, and then in another half, in another 1.9 hours, the half of the half, right? So the quarter remains and so on. So thinking about this, you know that your model for decay is this. And this is your initial amount A. This is your amount of everything Y. And this is the time scale. So what you know here is that if you look at the limit and you let time go to infinity of your function a e to the negative kt, you see that you get 0. Ooh, what does this mean for medications? Do we have anyone over here who's infinitely old? Because if you are, that means you have nothing in your bloodstream right now. See that? Yeah. Will this ever decay? Yeah, it's going to take 10,000 years to get the half of it, and then another 10,000 years for another half of the quarter, and then... The what? No, sorry. Planet Earth has a shelf life, so... Yeah, you didn't hear about that? We talked about it last class. So, yeah. So this is your exponential decay, and if you take a look at the two ends of the graph, the left-hand side of the graph is the end behavior that goes up to positive infinity. The right-hand side is supposed to go to 0, but it's 0 at infinity. So there is a horizontal asymptote for these at y equal 0, the x-axis. That also helps with the fact that exponential equations do not have a solution in terms of, you know, e to the x equals 0 or e to the x equal to some kind of negative number, because they don't cross the x-axis. So yeah, not important for this. We'll come back to this in Calc 2, so stay tuned. And yeah, that's it. We'll just say bye, right?